Good afternoon, and welcome to the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. I'm Mike Buckley, and we're coming to you live from the Van Allen Probe's Mission Operations Center here at APL, where we've just begun the final thruster burn for the Van Allen Probe Spacecraft A. Now this burn, which will last a little more than 2 hours and wrap up at around 6:27 p.m. Eastern Time, is the final deorbit maneuver for these twin spacecraft, which have been in orbit around Earth since August 2012. Their mission? Explore the radiation belts and the extremes of space weather. Now today we're going to talk about those radiation belts, the incredible mission to explore them, and the deorbit maneuvers for the spacecraft that we actually began back in February. Now to talk about this and answer these questions are Van Allen Probe's project manager, Nellie Masavi from the Applied Physics Laboratory, Van Allen Probe's project scientist, Sasha Okorsky, also from APL, and Geospace mission scientist Dave Sybeck from NASA Goddard Space Flight Center. Now we'll be taking your questions throughout the program, and we invite you to send them to us on various social media channels using the hashtag AskNASA. But Dave, we're going to start with you, and just first tell us about the radiation belts.
Well, Mike, the Van Allen radiation belts are two donut-shaped regions nested inside each other, one inside the other, circling the Earth. Their altitude starts from about 400 miles above the Earth's surface and extends out to about 1/10 of the distance to the Moon. They were one of the first discoveries of the space age. Professor James Van Allen from the University of Iowa flew a rocket up, the United States' first mission to space, Explorer 1, and it carried a Geiger counter. And that Geiger counter went off scale when the spacecraft went up into the radiation belts. And right then and there, Van Allen exclaimed, "Space is radioactive, highly dangerous."
Van Allen, too. Also did spend some time at the Applied Physics Laboratory, which was an honor to name the spacecraft after him as well. So, Sasha, let's talk about, man, we know about the belts, but why explore them? What's the importance of a mission like Van Allen Probes?
So there are two reasons for that. One is fundamental science, and that is very important practical reason. So the science challenge is that the intensity of radiation belt varies dramatically in response to energy input to the sun. It's shaped by a number of complicated physical processes that can produce losses and acceleration of the radiation belts, which makes it very challenging physical system to understand. And we now know that radiation belt type structures exist at all magnetized bodies in our solar system and probably across the universe. So here near Earth, we have a natural laboratory to understand and predict these processes. And second is very important, as I've said, practical reason. So Van Allen belts is the second Living with a Star NASA program mission, which goal is to understand adverse effects of space weather on life and technology at Earth. Speaking about life, so we just today happened Space Weather Walk that two astronauts undertook a few hours ago. So these radiation belt particles provide very dangerous environment for human explorations of space. And the same is for the spacecraft. An individual particle can damage dramatically both electronics on the spacecraft, which makes it very important for us to understand and predict this environment.
Okay, and so sending spacecraft someplace where they've never been before, it really shouldn't go, right? But now, Nellie, the Van Allen probes were built right here at APL.
Correct.
So tell us, so how do you build spacecraft to survive in this environment for so long?
So the good thing was that we knew where we were sending our spacecraft. So we knew that it's the harshest environment that a spacecraft is going. So we wanted to make sure that the spacecraft we built is kind of like a bulletproof, because it's constantly bombarded with these high energy protons and electrons. So what we did, we decided to make every instrument, subsystem in a hard shielding. So everything is shielded, about 1/4 inch to 1/2 inch of shielding. Again, like the blankets that covers the spacecraft, all the materials, they were all tested rigorously to make sure that they can survive those environments. So it was a lot of design consideration, a lot of collaboration between the different fields to make sure that they can use those materials tested. So testing, design, and collaboration between the instrument team and the scientist was the key component to make this mission a very successful mission that can not only tolerate 2.5 years that we were supposed to, but 6.5 years we're operating with no problems, no hiccup, and we are still continuing as strong.
As a reminder, we built 2 of them.
Correct.
So explain why, we touched a bit on the video, but
Yes.
why did we build 2?
So it's really good to have 2 because one is spacecraft, it's constantly going on the orbit, and the second one, it's coming in a couple minutes later, and that will help our scientists to understand if the phenomena that they just measured, is it a space related or is it time dependent? So it's a really good way for our scientists to compare the results constantly.
Okay, so speaking of results, and so I'm going to throw this question, Dave, both to you and Sasha. Some of the findings and the data that those spacecraft have collected has been sort of incredible, to say the least. So maybe let's cover the bigger findings that we have in Van Allen.
Yes, Mike, it's been an exciting mission from start till now, and it's still more excitement to come. Before this mission, people thought of the Van Allen radiation belts as kind of quiet regions, dangerous, but always the same from day to day, looking about the same. This mission immediately upon launch found that they're subject to dramatic changes. They could disappear within a matter of hours, could be replenished only a few hours later. There could be 3 belts, not the 2 that we traditionally thought. There could be 4 or even more. It's a much more dynamic environment than we ever dreamed of.
As David mentioned, from day one, we were shocked in a very pleasant, for a scientist, way by making a number of unprecedented scientific discoveries that now, 6.5 years later, completely rewrote the textbook on how Van Allen belts operate. In a sense, previously, it was considered a relatively simple system governed by a competition of 3 or 4 main physical mechanisms. And we now understand that the complexity of this system is really overwhelming. We discovered new physical processes that can interact and produce radiation belt energy particles on the timescales of minutes and seconds rather than hours and days, which we previously thought. Really dramatic and dynamic field.
And it also seems to drive home the point, too, about, I mean, this is pure exploration. I mean, it doesn't have to be to the extremes of the solar system or far out. This is pure exploration, close to home, but only enabled by sending spacecraft someplace where they haven't been before.
That's right. We've got lots to learn in our Earth's immediate environment, and that's what we've been doing with this mission. Yes, NASA looks at things from the sun to the Earth, but right in our environment, there were mysteries to uncover, discover, and solve.
Okay, so with spacecraft that have done their job and done it well, I want to start to talk about a bit about the maneuvers to deorbit the spacecraft. But first, let's just take a quick look to start the conversation with a video about the maneuvers and how they're going to happen.
Let's do that.
The Van Allen probes are powered from our solar panels, and so we need to make sure that the solar panels are always pointed towards the sun. The spacecraft will naturally precess, it'll move off of the sun, and we use the propellant in order to push the spacecraft back to make sure that it maintains that attitude. Once we run out of propellant, we don't have that ability to control the spacecraft attitude anymore.
We are using actually a large amount of fuel to change this orbit from 370 miles to 190 miles.
Each burn is 2 hours long, and we'll be using a little under 4.5 pounds of propellant.
And since we have fuel now, we need to deorbit, change the perigee closer to Earth to make sure in the next 25 years we are down.
Okay, so I guess that was a little bit too about why they're happening as well. So maybe a little bit more about how. I mean, we're here in mission operations, right?
Yes.
We're watching their people at consoles, and it's happening right now. So maybe describe some of the process about how we make these maneuvers happen.
Our spacecraft were in a very stable orbit. So why we wanted to change the orbit, we didn't want to create more space junk. So it's our responsibility to make sure that the next generation have the opportunity to actually explore the space as well. So in order to do that, we wanted to change our perigee from 370 kilometers to 170 kilometers. And we did that in 5 different steps. And the reason we are doing it in 5 different steps, it's because our thrusters were never designed to do a large duration of maneuvers. So we had to break it into 5 2 hours maneuvers, and each of them they use plenty of fuel, about 2.5 kilograms of fuel that they use. So really because of the thrusters that were not designed to do a large maneuver, we had to break it in 5 different maneuvers to do that.
Okay, too. And even the amount of fuel that the thrusters use at a different time, we're not talking about very large thrusters. I mean, these are
Oh, no, they are
inches.
very small. Actually, I would like to talk about the spacecraft. I mean, the spacecraft itself, it's not really large. And the thrusters, we have 8 thrusters that are not really big. We are using 2 of them each time that we are doing the maneuver. The spacecraft, it's about 6.6 feet tall and 6.6 feet wide. But what is amazing is these long booms that it has. It can cover like a football field. They are 50 yard long each, 40 on the sides, and 2, 12 yards. So, and the reason we had long booms, we wanted to make sure that they are so far away from the spacecraft that the electric field and magnetic field that they are measuring, it's really from the space, not from the spacecraft itself. So it's a very amazing spacecraft.
Resilient, we know that too.
Yeah.
I guess for scale, right? We wouldn't be able to do that in here to show this. But,
Right.
Something else that's incredible about this, we've had the details of the maneuvers themselves, but they'll be doing science on the way down too,
Yes.
isn't just let them go. This is another area where we haven't explored before, so maybe you could walk us through what we're going to be doing in this area of space.
Right, to start off a little bit again, to remind what the spacecraft orbit is at the perigee, which is the closest approach of the orbit to the Earth. It used to be only 370 miles approximately, and we're lowering it, but seemingly very little amount. We're bringing it only, changing it by about 200 miles, right? So it doesn't seem to be a large distance, but it brings us in a completely different space environment, which is not the outer space, but rather is the outermost layers of the atmosphere, where the drag is actually going to enable us to deorbit eventually, right? So this is the region where most of the spacecraft avoid for exactly the same reason. They want to stay on orbit rather than get down. And we will continuously be taking data for another 9 months or so if everything goes along as we predicted. Hence, we're going to sample and provide new data from the region of space that is really not really well measured at this point. Specifically, for instance, this is where close to the region where the low Earth orbit of the spacecraft is. And we're going to provide amazing data of the inner edge of the inner radiation belt, one of the most hazardous environments where the highest energy particles in the radiation belt reside. So these data will be a completely new data set. It also is going to give us a very interesting engineering point, because again, our sensors and instruments were not designed to operate in these regimes, and so like we're going to get new engineering data, which is going to provide us with some new data in order to build and improve our space instrumentation for fundamental science and exploration. So really exciting.
So can I ask a practical question? Like, so where are they headed? Where is it going to go after this time in 25 years?
So that's a really good question. We get that question a lot. So we don't know exactly when it's coming to re-enter, but we know in less than 25 years, most likely in 15 years, it will re-enter and it will burn up. It won't fall in anyone's backyard. It will be not like it's been big chunk pieces. So it will be completely burned up as it re-enters. So, but in less than 5 years, that's what's going to happen. It re-enter the atmosphere.
Which is a very sad moment for us.
I bet. I can imagine see that, right? I mean, there's different parts where sometimes when the spacecraft launches, the engineers say, oh, there it goes. And then after years of operations, like we're seeing here, at some point, you have to let go after this.
Yeah, like 6.5 years. It's actually very considerable time with the entire generation of scientists grew up studying this data.
For a mission that was supposed to last 2 years?
Yeah.
2.5 years.
Right.
So this mission has been operating also at APL as well. So we need to give a shout out to our 18-meter dish guys who've been operating the spacecraft non-stop and providing 3 times more than the data that was required to our scientists every day. So that was amazing.
It's a remarkable mission, too, in those cases. So again, a reminder to everybody following us, please send your questions using the hashtag #NASA, and we're going to start getting to them soon, and then even try to address some of them after the program if we don't have time for them, because my iPad's lighting up with questions. We'll try to get to some of those too. But Dave, I want to ask you another thing. We've talked specifically about the Van Allen probes and the science that's happening in the radiation belts, but where does this mission fit into the larger picture of what NASA is studying between that Sun-Earth connection?
Well, Mike, the Van Allen probes are like the focal point of an armada or fleet of spacecraft that NASA's heliophysics division has launched to study everything that's happening from the core of the sun all the way down to Earth's atmosphere. There's an invisible chain of events that links things from the sun to the Earth. Vast solar flares blow out large amounts of plasma particles from the sun that come to the Earth and bombard the Earth's magnetic field. In response, the Earth's radiation belts that Van Allen probes is studying can build up, energize, become intense, or they can be blown away and just disappear within a matter of hours. So we here, looking at the Van Allen probes data, are looking at the dynamic consequences of things that happen far away on the sun. We're looking at them in a place so they can do damage to our spacecraft and harm our astronauts. A very crucial mission for NASA.
So let's just start going to the questions now. Here's one from Facebook, and I'm going to take a different spin on this one too. But you've talked about that the radiation belts are dangerous. May you explain a little more like why they're dangerous? I mean, we talked about particles and hazard, but a little bit more about why they're dangerous, especially if somebody was operating them.
Okay.
So this is a form. Okay, so let's go a little bit more. Very good questions, by the way. Let's go a little bit more into physics. So what are radiation belts? So these are charged particles, electrons and protons mostly. They're accelerated to incredibly high energy. What do we mean by that? We can say that it's mega electron volts or so, but it means that they travel at a very high speed, which is approaching the speed of light. So a single particle can penetrate through spacecraft shielding, or sadly through our body, and produce ionizing radiation, break up particles, molecules, and atoms inside our body, and produce the same damage as is done by radiation that we know it on Earth.
So we take cautions and maneuvers and moves to, for both spacecraft and people in the space station in order to be behind shielding there. Have we learned enough, or can we say what we've learned from the spacecraft to say build that next generation of radiation-hardened spacecraft that could survive in this environment? Have we learned enough yet, or that we can?
Yes, we have learned a lot. Like in the 6.5 years that we've operated with different environments, many geostorms that we have experienced, 6.5 years that we've been through the solar cycles. We've looked at all these different changes in our spacecraft, and we know exactly what thickness of shielding, for an example, is required. How do we need to build and the next generation of the spacecraft? So, and our the good thing is that our resources are open to everyone. A lot of people have used it. They published papers. About 560 just journal paper has been published using our data. So we have learned a lot from operating this our two spacecraft in the last 6.5 years.
Right, so it's not just rewriting the books on the belts themselves, but it's about how things survive in there.
Yes.
Right, but just to put it a little bit in a practical context, so there was no single mission before that survived in radiation belts, in the heart of radiation belt intensities, for as long as we did. So hopefully by the end of the mission, we will collect more than 7 years of data. What does that mean? It means that we covered more than half of 11-year solar cycle. So we understand now and can quantify not only how the radiation environment changes in the response to specific solar storm or solar flare, we now can put it in the context and say how the radiation belt dynamics changes during different phases of the solar cycle. It has never been done before.
Smaller question too about where are the spacecraft in their orbit? How far apart are they from each other? This was a question from Facebook.
Sure. They are, they are not exactly on the same orbit. They are, we have the picture, I don't know if we have the picture on the monitor, but so they are not exactly on the same orbit. They have a little bit shift from each other. And about a couple minutes that it takes that one spacecraft reaches to another spacecraft. Do you have a better?
The spacecraft are trailing each other, so the orbits are very similar, and they lap each other. So this was done intentionally, so the spacing between the two spacecraft changes with time, which allows us to sample and understand different scale sizes and different mechanisms and processes in space. So every 30 days approximately, one spacecraft overtakes another. So we provide kind of different temporal and spatial quantification and resolution of what's happening in the system.
Okay. I'm going to combine some questions here because we have time for one more on this, because I'm seeing a theme in some of these. But just as for each of you, what has been the biggest surprise? I think that you've the discoveries for this mission 6 years, maybe the biggest surprise that you've seen.
Well, these were the most completely instrumented spacecraft that ever went to the radiation belts, and as a result, they've shown us more than we could ever imagine. And the single biggest surprise for me was just how dynamic the radiation belts are, how quickly they could change, appear, disappear, and the arguments that we've seen amongst the scientists trying to figure out what mechanism is the right one. And it turns out a lot of mechanisms are right. Everybody's right. So every mechanism plays a role. It's been a really fascinating mission.
Just to probably just concur and add a little bit more to what David said, it's just not one specific discovery, but a multitude of unexpected discoveries. We made a discovery almost on the first day when the instruments got turned on, and we still keep making fundamental discoveries and unveiling mysteries that have never been imagined before. So not only we understand the system more, we also know how much we don't understand. So this is our plug for more space missions, I guess.
For me, as an engineer, it's more about like how we built these spacecraft resilience to environment. And now that we know how harsh these environments are and how dynamic they are, and the two spacecraft, they were able to actually be so resilient and work and function every day in these environments. That was the most impressive thing, and I think the team overall is so proud of what we've accomplished and the operation and design, all different stages of the.
Yeah, it's been a wonderful partnership between NASA and JHU APL.
And other 5 institutions who provided us science instruments and are responsible for the success that is coming out of the mission.
Well, thank you all for answering these questions on the panel. They're still ready to follow this mission online. And first, we'll just take one more look at this incredible mission through a video. And thank you for joining us.
The Vanilla probes right now are in a stable orbit. And if they remained there, they could be in orbit for hundreds or thousands of years.
Because there's nothing to slow them down, there's nothing to remove energy from their orbits.
All of the missions now need to deorbit their spacecraft at the end of their lifetime so that we don't end up with space junk. We're performing a series of maneuvers on the Vanilla probe spacecraft in order to change the orbits.
Next year, we won't have enough fuel to do this kind of a maneuver. This is our only chance to get our spacecraft to the orbit that we want.
The Van Allen probes have really provided us with more than 6 years of non-stop excitement, continually bringing us wonderful science results, incredible observations from the heart of the most intense radiation region that really humanity has ever found.
The radiation belts exist across the solar system and probably across the entire universe at all bodies that have their own magnetic field like we have at Earth.
But they are very, very susceptible to changes in the solar wind.
During geomagnetic storms, they can completely disappear and then come back with much, much higher intensity.
So spacecraft that aren't normally in them can suddenly become engulfed by them. And so it's really critical for us that we understand how these radiation belts are changing so we can better design spacecraft to be able to withstand unexpected dosage of radiation.
So understanding the fundamental science is absolutely required in order to make predictive model relevant to space weather.
Having the 2 satellites, you get 2 simultaneous measurements of different parts in the belts, and that gives more of a global picture of what's going on with solar weather and with the radiation belts over time.
Their orbits are a little bit shifted, so instead of having them overlay on top of each other, they're moved a bit to the side.
We try to plan and create opportunities for them to pass near to each other, which presents an opportunity for the scientists to have short-range correlation of the data and also to take measurements along the same magnetic field line.
We have this highly elliptic orbit in order for the spacecraft to go through all of the different areas of the Van Allen radiation belts. So it really gets a great picture for the scientists of what's going on in the different regions.
The Van Allen radiation belt probes have really shown us just how dynamic and how exciting this region of space is.
And prior to our mission, were considered as a relatively boring and uninteresting and well understood field. Our mission turned it completely around and made it into a complete new science exploration, vibrant field by making a number of unexpected scientific discoveries.
We actually launched them. We really thought they were just two belts. Very soon after we launched, we discovered that the outer belt can actually split and form two belts itself, giving us a three-belt structure. But we were able to really watch how that third belt formed, how it changed, and then eventually how it diminished and just sort of got sucked back into the original radiation belt.
Over the course of the mission, we've taken over 8,500 contacts, and that's about 18,000 hours of contact time. Because the dish and the Mission Operations Center are co-located at APL, we have a lot more time available on our antenna.
We not only downloaded every day 3 times more than the science data that we were required to our scientists, we published about 560 papers across the globe.
Right now, every 3 days, someone in the world is publishing a paper based on the Van Allen probe's data.
The Van Allen probes are powered from our solar panels, and so we need to make sure that the solar panels are always pointed towards the sun. The spacecraft will naturally precess, it'll move off of the sun, and we use the propellant in order to push the spacecraft back to make sure that it maintains that attitude. Once we run out of propellant, we don't have that ability to control the spacecraft attitude anymore.
We are using actually a large amount of fuel to change this orbit from 370 miles to 190 miles.
Each burn is 2 hours long, and we'll be using a little under 4.5 pounds of propellant.
And since we have fuel now, we need to deorbit, change the perigee closer to Earth to make sure in the next 25 years we are down.
These are by far the largest maneuvers we've done to date.
We're going to be executing 5 burns over the course of 2 weeks when the orbits are in the proper orientation to really have the most efficient burns possible and save the most propellant to be able to do science as long as we can.
The fact that the spacecraft and those instruments have survived more than 6 years in really what is the most intense radiation region that we know is just incredible.
This mission was about resiliency in the harshest environment that no other spacecraft was able to take. This mission was making the impossible possible. And we really did it by a great, talented team that we had, the hard work that they put, and the collaboration across different disciplines to make this happen. And we really couldn't be more proud of what we've accomplished.